Welcome to Multi-Roam Academy Foundations. In this tutorial we build something most single-cell courses skip entirely, a clean, isolated, reproducible Python environment. Take your time here, because everything you analyze later depends on getting this one thing right. Here's our roadmap. We start with why environments matter at all, then install conda properly. We create and manage environments, understand channels and package installation, wire up 𝗪𝗏, make everything reproducible, and finish with the errors you'll actually hit and exactly how to fix them. No computer science background required. This is written for biologists, clinicians, and computational newcomers, anyone moving from the bench to the keyboard. If you've ever cloned someone's code and watched it fail on your own machine, this tutorial is the fix. We assume no prior experience with the command line, and we explain every decision as we go. Everything here runs in a terminal, a text prompt where you type a command and press enter. 3 commands cover the basics. pwd shows where you currently are, ls lists what's in the current folder. And cd moves you into another folder. That's genuinely most of what you need. The rest of this tutorial is just typing conda commands at that same prompt. Part 1. Before a single command, let's understand the problem we're solving. Once it clicks, everything else follows naturally. Python is 2 things, a language you write and an interpreter, a program that reads your code and runs it. When you install Python, you're really installing that interpreter. An environment bundles a specific interpreter with a specific set of packages, which is why pinning the Python version matters just as much as pinning your packages. A package is a reusable bundle of code someone else wrote and shared, so you don't have to reinvent it. 𝗀𝗵𝘃 is a package. NumPy is a package. Installing one downloads that bundle and its dependencies into your environment. Almost all modern analysis is really just assembling the right packages, which is exactly why managing them well matters so much. Real analysis pipelines stack dozens of packages, and each one depends on others, at specific versions. 𝗀𝗵𝘃 needs a certain NumPy, another tool needs a different one. Install everything into one shared Python, and those requirements collide. The result even has a nickname. Dependency hell, where fixing one tool quietly breaks another. Picture 2 projects. Last year's used an older NumPy, today's needs the newest. Share one Python between them, and upgrading for the new project silently breaks the old one, the exact code behind your published figures. Isolation means each project keeps the versions it was built with, permanently and safely. In science, an analysis you can't reproduce isn't finished. Reviewers may ask you to rerun it a year later. A collaborator needs your exact setup. Future you, on a new laptop, has to pick it back up. A defined environment turns, "It worked on my machine," into, "Here's the machine, run it yourself." An environment is a sealed room with its own Python and its own packages. What happens inside one rune can't touch another. You can keep a rune for single-cell RNA work, another for spatial analysis, another for a class, each with different, even conflicting, versions. Conda is what builds these runes and switches between them. These 3 names confuse everyone at first, so let's separate them. pip installs Python packages from PyPI, but it does not manage environments. Then, built into Python, creates isolated environments, but only for Python. Conda does both at once, and crucially it also installs the compiled, non-Python libraries that bioinformatics tools depend on. That's why we lead with conda. Part 2. Installing conda and choosing the right flavor, because that choice saves you real pain later. Conda comes in 3 common distributions. Anaconda is a giant bundle of hundreds of packages, heavy, and with licensing limits for larger organizations. Miniconda is stripped down, but points at Anaconda's default channel. Miniforge is also minimal, but defaults to the free, community conda-forge channel. For single-cell work, Miniforge is the one I recommend. Start lean and pull in only what you need. conda-forge is a community-maintained collection of conda packages, broad, current, and consistently built to work together. Nearly every scientific and single-cell package you will want lives there, kept up to date. Miniforge uses it by default, which quietly prevents a whole category of dependency conflicts before they ever start. Anaconda's default channel is free for individuals and small teams, but larger companies and institutions may need a paid license to use it. This is a big reason Miniforge and conda-forge have become the community standard. They sidestep the question entirely. If you're at a large organization, Prefer conda-forge to stay on the safe side. Installing is 3 steps. Download the Miniforge installer that matches your operating system and chip, for example Apple Silicon versus Intel. Run it in your terminal and accept the defaults. Then close and reopen the terminal so the changes take effect. On Windows, you run the graphical installer, then use the Miniforge prompt it adds to your start menu. Let's confirm the install. Run conda-version to see the version number, and conda info for a fuller picture of your setup. The clearest signal, though, is your prompt itself. It should now begin with the word base in parentheses. That tells you conda is active, and you are sitting in its default environment. One habit worth forming early: keep conda itself up to date. This command updates conda in the base environment from a conda-forge. A current conda means the fast solver and the latest fixes. And note, we're updating conda the tool here, which is the one thing it is perfectly fine to touch in base. You'll hear people mention 𝗪𝗵𝘁. It's a drop-in replacement for conda that resolves and installs faster. Install it once into base, then simply swap the word conda for 𝗪𝗵𝘁 in your commands. Modern conda already uses the fast 𝗪𝗵𝘁 solver, so the gap has narrowed, but many people still prefer 𝗪𝗵𝘁 speed and clearer output. The base environment exists to run conda itself and nothing else. If you install project packages into base, you slowly corrupt the one environment that manages all the others. Treat base as off-limits. Every project gets its own room, which is exactly what we build in the next part. When you install a package, conda solves a puzzle: which versions satisfy everyone at once. Modern conda ships with the 𝗪𝗵𝘁 solver by default, which does this far faster than the old one. If an install ever feels stuck for minutes, an outdated conda is often the reason, so keep conda itself current. Part 3. Creating and managing your environments. These are the day-to-day habits you'll use on every single project. Now we build a room of our own. Conda create makes a new environment. The -n flag names it 𝗺 brain for a single-cell brain project. We pin Python to 3.11 so the version is explicit and repeatable. The -y simply accepts the prompts. Pick a name that means something to you: the dataset, the paper, or the analysis. You don't have to create an empty environment and fill it later. You can name your packages right in the create command, and conda solves them all together as one consistent set. This is often cleaner than installing piece by piece, and it's a great pattern once you know which tools a project needs up front. Leave the version off, and you get whatever Python is newest that day, which drifts over time and across machines. Pinning to 3.11 means you, your collaborator, and a server 6 months from now all get the same interpreter. Many tools also lag the very newest Python release, so a slightly older, stable version is often the safer choice. To use an environment, you activate it. Conda activate 𝗺 brain steps you inside, and your prompt updates to show the active room, so you always know where your code is running. Everything you install now lands here and nowhere else. When you're finished, conda deactivates steps back out to base. Get in the habit of checking that prompt before you install anything. 2 commands you'll use constantly: conda-env list shows every environment you've created and marks the active one with an asterisk. Once you're inside an environment, conda list prints everything installed in it, with versions. When something misbehaves, these 2 are the very first place to look. Want to try a risky upgrade without endangering a working setup? Clone it. This makes a complete copy under a new name, so you can experiment freely. If the experiment works, keep it. If it breaks, delete the clone, and your original isn't touched. Cloning is the safe way to test changes before they matter. Named environments live together in one folder conda manages, usually under your home directory, in a folder called ends. You rarely touch it directly. Conda-env list shows you the paths. Knowing they're just folders demystifies everything. Removing an environment simply deletes its folder, which is exactly why it's so safe and so cheap to throw one away. Because each environment is self-contained, it's also disposable, and that's liberating. If one gets tangled beyond repair, don't fight it. Deactivate, remove it with conda-env remove, and rebuild from your environment file in about a minute. Throwing an environment away costs you nothing, which is exactly why isolation is so powerful. Part 4. Channels and installing packages. This is where most beginners hit their first real wall, so let's walk right past it. A channel is a source that conda downloads packages from. For single-cell work, 2 matter most: conda-forge, home to the core scientific stack, and 𝗵conda, home to bioinformatics-specific tools. You can name a channel per install with -c, or set your defaults once, so you never have to think about it again. 𝗵conda is a channel dedicated to biology tools, aligners, samtools, and thousands of others, many with tricky compiled dependencies. It's built to layer on top of conda-forge, which is exactly why we set conda-forge as the higher priority. Together, the two channels cover almost everything a single-cell or genomics project will ever need. Run these 3 lines once, right after installing. They tell conda to prefer conda-forge, then 𝗵conda, and to enforce that order strictly. Strict priority is the single most effective setting for avoiding the slow, tangled installs beginners dread. Note the order. Whatever you add last becomes highest priority, so conda-forge ends up on top. Both conda and pip can install Python packages, but mixing them carelessly breaks environments. The safe rule: install everything you can with conda first, and only reach for pip for packages conda doesn't have. When you do use pip, use it last, after your conda installs are settled, and avoid conda installing more afterward. When you find a new tool, check its documentation. Most list install command directly. If it shows a conda-forge or 𝗵conda command, use that. If it only shows pip, use pip inside your active environment. When both exist, prefer conda for consistency. The docs almost always tell you which path the authors actually support. With 𝗪 active, install the core toolkit. 𝗪𝗵 is the backbone for single-cell analysis in Python, and it pulls in and data, the object that holds your cells and genes. Python graph and 𝗵𝗃 provide the graph and clustering machinery 𝗪𝗵 leans on. One command, from conda-forge, and the heavy lifting is done. You can be as precise as you like about versions. A single equals with conda pins a minor series. A double equals with pip pins an exact version. Greater than or equal sets a floor. For everyday work, loose pins are fine. For a result you must defend, pin exactly. The tighter the pin, the more reproducible the environment. Environments aren't frozen. We'll adjust them over time. Conda update brings a package to a newer version, solving the rest around it. Conda remove takes one out cleanly. Make these changes deliberately, and re-export your environment file afterward, so the recipe always matches what you actually have. Occasionally a tool lives only on 𝗵PI, some deep learning models, or a niche method from a recent paper. That's what pip is for. With your environment active, pip install places the package inside this environment, not system-wide. You can pin an exact version with a double equals syntax, which you'll want whenever a result must be reproducible. Sometimes a bug fix or feature exists only in a package's development branch, not yet released. You can install straight from GitHub with pip and a git plus URL. Use this sparingly. Development code changes without warning, but when a reviewer's fix landed last week and you need it now, this is how you get it. Part 5, 𝗪𝗼, where you'll actually write and run your analysis, plus the one step almost everyone gets wrong. Notebooks are ideal for exploration. You see each result as you go. Plain Python scripts are better for pipelines you'll rerun end to end. VS Code is an editor that does both, and talks to conda environments directly. Start in notebooks while you're learning, and reach for scripts and an editor as your work matures. Most single-cell work happens in notebooks, where code, output, and figures live together. Install 𝗪𝗼 into your environment from conda-forge. Installing it inside 𝗪𝗃, rather than globally, keeps it aligned with the exact packages this project uses, which matters more than it sounds, as the next slide shows. Here's the mistake that costs beginners hours. 𝗪𝗼 can run under a different environment than the one you activated, so your carefully installed packages appear to be missing. The fix: install 𝗵𝗃, then register this environment as a named kernel. Now 𝗪𝗼 offers Python 𝗪𝗃 explicitly, and you can be certain your notebook is using the right rune. Start it with 𝗪𝗼, and your browser opens the workspace. Create a new notebook, and in the top right corner choose the kernel named Python 𝗪𝗃. That selector is the moment of truth. It decides which environment your code runs in. Confirm it every time you open a notebook, and you'll sidestep the most common source of confusing errors. Here's a first taste of the workflow you're enabling. Import 𝗪𝗵, read a single cell file into an AND-data object, and display it. For a brain cortex dataset, you'd see the number of cells and genes, and the metadata attached to each. Every analysis you'll ever run starts almost exactly like this. Setup done. The science begins. Before trusting anything, verify. In your notebook, import 𝗀𝘁 and call print header. It prints 𝗀𝘁's version alongside its key dependencies, NumPy, pandas, and the rest. A clean version table with no errors means every piece is talking to every other piece, and you're ready to load your first brain single-cell dataset. Part 6. Reproducibility. This is the difference between a project others can rerun and one that quietly dies on your old laptop. Now capture what you built. Conda int export writes every package and version into a single file, environment.yaml. Commit that file alongside your code. It's a complete recipe for your setup, the one artifact that lets anyone, anywhere, rebuild the exact environment your analysis ran in. You'll see both. A requirements.txt lists pip packages only, which is fine for pure Python projects. An environment.yaml captures the whole conda environment, including the Python version and the non-Python libraries, and it can hold a pip section too. For single-cell work, the environment file is the more complete record, so prefer it. A plain export records exact builds tied to your operating system, so it may not rebuild on a different platform. Adding -- from history exports only the packages you explicitly requested, without the machine-specific build strings. That version is far more portable across Mac, Linux, and Windows, and it's usually the one you want to share. This is the payoff. On any machine, conda int create with -f reads the file and reconstructs the whole environment, same packages, same versions. Your collaborator runs one line and is working in minutes, not debugging installs for an afternoon. This single step is what makes a shared analysis actually shareable. An environment file is only useful if others can find it. Commit it to your project's Git repository, right beside your code and notebooks. Now anyone who clones the project gets the exact recipe to rebuild your environment. Code plus environment file plus data is the full package for reproducible science. For the strictest reproducibility, a clinical pipeline or a published result you must defend, a tool called conda records the exact build of every package, including dependencies you never named. It produces a lock file that rebuilds bit for bit across machines. It's optional, but it's the gold standard for when close enough isn't. Part 7. Troubleshooting. Here's the handful of errors you will absolutely see, and the calm, correct response to each. If your terminal doesn't recognize conda at all, the installer setup step didn't finish, or you simply didn't reopen the terminal. The fix is usually to close and reopen it or to run condas in its step once, so your shell knows where conda lies. After that, the base prompt returns and everything works. This means conda searched your configured channels and couldn't find the package. Usually the fix is a channel, the tool lives on conda-forge or bioconda, and you haven't added it. Add the right channel, or double-check the spelling. If it truly isn't on conda at all, that's your cue to fall back to pip. If installs crawl or report unsolvable conflicts, 3 things usually help. Make sure channel priority is strict. Update conda, so you have the fast 𝗵𝗵𝗁 solver. And install related packages together in one command, not one at a time, so conda can solve them as a set. Creating a fresh environment often clears a stubborn conflict instantly. You installed the package, activated the environment, yet the notebook insists it's missing. 9 times out of 10, the notebook is running a different kernel. Check the kernel name in the corner, select Python-SC brain, and rerun. If it's still missing, confirm you installed it while that same environment was active. Over time, conda's cache of downloaded packages can grow to many gigabytes. Conda clean -- all safely removes those cached archives without touching your environments. Run it occasionally. And remember, deleting an unused environment you can rebuild from a file is always safe, because the recipe lives in your environment.yaml. Part 8. Let's put the whole thing together and point you at what comes next. Here is the entire workflow at a glance. Install Miniforge, set strict channel priority, and create a named environment with a pinned Python. Activate it, install your stack with conda, and use pip only for the exceptions. Register the 𝗃𝗿𝗃𝗃 kernel, verify with print header, export your environment file and rebuild anywhere from it. Do this once, and it becomes second nature. With your environment ready, the real work begins. Next in Foundations, we'd open the AND data object, where your cells, genes, and metadata actually live and start turning raw counts into biology. You've built the workshop. Now we pick up the tools. That's your foundation. Clean, isolated, reproducible, ready before the first line of analysis. Everything you build from here stands on it. This was Multi-Roam Academy Foundations. Stop running code you don't understand, and I'll see you in the next one.